Hello my dear students. In this class we are going to see some examples on orthogonal linear transformation. So we have to show that this example on the screen is what? Orthogonal linear transformation, right? So now there are two ways to prove it. The first way is, first of all, we will show that uh, it satisfies म्हणण्यापेक्षा it preserves the inner product, in the sense we are supposed to show that inner product of tx with ty is equal to what? Inner product of x with y for all xy belonging to V if t is a map from V to V. The first thing, and then second thing, we are supposed to prove that t is a linear transformation, because in the question it is only given that it is a map. This is the one way, but instead of using this method, we are going to go for what? The theorem that we have proved in the last class. So basically solving these examples is nothing but application of last theorem that we have discussed. So what is the last theorem saying? Let us go back. Yes, so if V is a finite dimensional inner product space, and if f from V to V is a map such that these two conditions are satisfied, then we can say that f is a orthogonal linear transformation, right? So now in our problem, our V is finite dimensional, no issues with that, because our V is R2, and I will show you. Yeah, so this is our example, right? So you can see that our V is R2, so which is finite dimensional, and T is a map. So now if we are able to prove these two conditions, what are the conditions of our theorem? Yes, so if we are able to prove these two conditions, first one is, now over here the notation f is used for function, but in our example it is t. So if we are able to prove t of 0 is equal to 0, and the second thing is, if we are able to show t is isometry, then we can directly say that t is orthogonal linear transformation. Okay, so it is much easier than going for what? The usual definition of orthogonal linear transformation. So we are going to use this theorem. Okay, so remember these two conditions. First of all, 0 fixes 0 is mapped to 0, and the second thing is it should be an isometry. Okay, so same thing we will do over here. Okay, for this example, so just I will erase it out. So solution here, our V is nothing but R2, right? So which is finite dimensional. So in order to show T is orthogonal linear transformation, the first thing is T of 0 is equal to 0 comma 0. See, that condition will be easily satisfied. Okay, because if you put x is equal to 0, y is equal to 0, you are going to get a 0 vector. I hope you understood this, because this is how our 0 vector of R2 looks, right? And the second thing is, what we are supposed to prove, T is an isometry. Okay, so first, so no issues, clearly we are having this. So याच्यात काय प्रूव्ह करण्यासारखं नाहीये. Okay, so now we are going to prove T is an isometry. Okay, now as we have already seen examples on isometry, so it will be easier now. So in order to show certain function is isometry, we need two vectors, right? Or you can say two elements of domain, that is R2 in this case. So I will say I will use the notation z1 is equal to x1 y1 and z2 is equal to x2 y2 belonging to R2 be any elements. So what we are going to show, I hope you remember, first of all we show that norm of T of z1 minus T of z2 square is equal to what? Norm of z1 minus z2 square, and then we will take positive square roots on both sides and we will get T to be an isometry, right? So without any delay, just I will start with the left hand side, but before that just let us see what will be our right hand side. Okay, so what will be my z1 minus z2? Z1 minus z2 will be x1 minus x2 comma y1 minus y2. So what will be my norm of z1 minus z2 whole square? It will be simply, now over here we are going to go for dot product. Okay, so if we are having some x is equal to x1 comma x2, so we already know what is our norm of x square. It is x1 square plus x2 square. Okay, take the products of the components or coordinates rather and simply add them. मग इथे पण तेच, सो इथे काय येईल x1 minus x2 whole square plus y1 minus y2 whole square. हे कशासाठी केलं आहे आपण? आता आपण लेफ्ट हँड साइड पासून स्टार्ट करणार आणि वी हॅव टू रीच टिल हियर. ओके, सो वन्स वी रीच हियर then that is nothing but what, this norm of z1 minus z2 whole square. Okay, so before that just I will make some space over here. So what is my LHS? Norm of T of z1 minus T of z2 whole square, which is further equal to norm of, put the value of z1 which is x1 y1 minus T of z2 is x2 y2 whole square, which is further equal to, so what is our function? T of xy is 3 upon 5x plus 4 upon 5y, so 3 upon 5 x1 now plus 4 upon 5 y1 comma, and over here we'll get what is the second coordinate? Let me see that. The second coordinate is minus 4 upon 5 x1, and what is the other one? Plus 3 upon 5 y, so plus 3 upon 5 y1. Okay, so this is for the T of x1 y1 only. Now we'll go for T of x2 y2, so this will be easier. This is simply 3 upon 5 x2 plus 4 upon 5 y2 comma minus 4 upon 5 x2 plus 3 upon 5 y2 nor square. Okay, so which is further equal to, simple calculations, norm. So this will be, so subtraction of first coordinates, so inside the bracket, so one can see this is 3 upon 5 x1, over here it is 3 upon 5 x2, so that 3 upon 5 can be taken common, so this can be written as 3 upon 5 is common. Inside the bracket what is left out? It will be x1 minus x2 plus, in a similar way I will take that 4 upon 5 out, and inside the bracket it will be y1 minus y2. Now this is the first coordinate, I hope you are getting. So this is a subtraction of what? This one and this one. Okay, so या दोघांचं subtraction आहे. Now for the second coordinate याचं आणि याचं subtraction येणार, but one can see that we are already having minus sign here, you can see. Okay, so this minus and this minus will be plus, so over here what we are going to get, 4 upon 5 common घेतल्यानंतर. Okay, so 4 upon 5 is out. Inside the bracket इथे येणार minus x1 आणि इथे येणार minus minus will be plus, so it will be plus x2 आणि plus 3 upon 5, this is going to be y1 minus y2. This is our second coordinate of a point in R2 whose square, so this is equal to, so what will be norm of this vector now? Okay, now see, this vector is of the type this one. Are you getting my point? X is equal to x1 x2, where what is your x1? Okay, so this is your x1, just a minute. Yes, so this is your x1, this is the first coordinate, right? And this is your x2, the second coordinate. right? So this will be, as you know, norm of x square is nothing but what? X1 square plus x2 square. So square of this plus square of this. So what will be that? Just I will take little bit down. So you will have over here, this will be equal to, so it will be 9 upon 25, or first of all I will write one more term. So x1 square will be a square bracket 3 upon 5 x1 minus x2 plus 4 upon 5 y1 minus y2 whole square. This is x1 square plus x2 square. So our x2 is 4 upon 5 minus x1 plus x2 plus 3 upon 5 y1 minus y2 whole square. Okay, so हे फक्त समजण्यासाठी होतं, so I will just erase it out. Okay, now simply doing some calculations. So square it. So a plus b whole square formula you have to use, a square plus b square plus twice ab. So this will be 9 upon 25 x1 minus x2 square plus 16 upon 25 y1 minus y2 square, plus twice ab. So it will be twice, our a is this, our b is this. So it will be twice 3 upon 5, this 4 upon 5, and multiplied by x1 minus x2 multiplied by y1 minus y2. Now these are the calculations for the first term. Now for the second term, plus 16 upon 25 minus x1 plus x2 square plus 9 upon 25 y1 minus y2 square and plus twice ab. So plus twice 4 upon 5 multiplied by 3 upon 5 minus x1 plus x2 multiplied by y1 minus y2. Okay, so let me make some space. I hope you are following what I am doing. The same issues you might have faced where, I mean issues in the sense, the homework examples I gave for isometries were these similar examples, right? So this is the trick that you were supposed to use in that examples. So now let us simplify it. So over here you are having x1 minus x2 whole square. Now somewhere in the other term also you might be having x1 minus x2 whole square. See this. Now one might say that this is minus x1 plus x2 whole square, but as I have told you in the last class, this minus x1 plus x2 whole square can be written as, if you take that minus out, so inside it will be x1 minus x2 whole square, and if you square it, it is same as x1 minus x2 whole square. So I hope you are getting my point. So x2 minus x1 whole square is same as x1 minus x2 whole square. So simply I am going to add them. So once you add them, the coefficients will be also added. So over here the coefficient is 9 upon 25 and it is 16 upon 25. So it will be 25 upon 25, which is 1. So here you are going to get x1 minus x2 whole square. Okay. Now coming to this term. So it is 16 upon 25 y1 minus y2 whole square. Over here you are having 9 upon 25 y1 minus y2 whole square. So again if you add them, you are going to get y1 minus y2 whole square. So plus y1 minus y2 whole square. And what about this term and this term? So this term and this term will get cancelled out, I guess. Yes, it will get cancelled out. What is the reason? I will tell you. Now see here, over here I am having x1 minus x2 and this is y1 minus y2. Now over here I am having minus x1 plus x2. So if I take minus sign common from here, so what I am going to get? So it is x2 minus x1 actually. So this is x2 minus x1. So if I take a minus common, what I will get? If I take minus common, it will be x1 minus x2, and this minus sign I will adjust here. Okay, so this is same as, see what I will do, minus, okay, and over here x1 minus x2. I hope you are getting what I have done. So therefore what is going to happen is this term and this term will get cancelled out, and therefore I think we got what we wanted, and this is nothing but norm of z1 minus z2 whole square. Okay, and therefore I can say that, therefore what we have proved, norm of t of z1 minus t of z2 whole square is equal to norm of z1 minus z2 whole square for all z1 z2 belonging to R2. Therefore now by taking positive square roots on both sides, so what you are going to get, norm of t of z1 minus t of z2 will be equal to norm of z1 minus z2 for all z1 z2 belonging to R2. Note that this is a comma. If you want, I will write it properly. This is also a comma. So therefore T is an isometry. I will call it as sum 2. And what is my one equation? My one equation is this. Where is that? Yeah, this. So therefore from 1 and 2 we can say that T is orthogonal linear transformation. Therefore from 1 and 2. Okay, so you are supposed to state that theorem. Okay, state it. I will write here in the exam if the question comes. Fine, now we will move towards second example, which is the similar one. So we are supposed to do the same thing over here. So in this example also our V is R2. So here our V is same, that is R2. So again I will write, in order to show T is a orthogonal linear transformation, we show, so there are no issues for the first condition clearly, 0, 0. Now we will go for what? The second condition. So in order to prove T is isometry, we need two elements of R2. So I'll select Z1 is equal to X1 Y1 and Z2 is equal to X2 Y2 belonging to R2, be any elements. And what we are going to show? To show over here norm of T of Z1 minus T of Z2 square is equal to norm of, okay, later on we'll take positive square roots and we'll get that T is a isometry. Now you might remember, what is our right hand side? Our right hand side is nothing but, just a minute, yes, so our right hand side is norm of Z1 minus Z2 whole square will be, I guess, X1 minus X2 square plus Y1 minus Y2 square. Okay, so there we are supposed to reach. So once we reach here, then we will get our right hand side. So I'll say consider norm of T of Z1 minus T of Z2 square. Now put the values of Z1 and Z2, so it will be norm of T of X1 Y1 minus T of X2 Y2 whole square, which is further equal to, now what is my T of XY? 1 upon root 2x plus 1 upon root 2y, and in the second coordinate we are having the negative sign, so this will be norm of 1 upon root 2 x1 plus 1 upon root 2 y1 comma 1 upon root 2 x1 minus, now right, 1 upon root 2 y1. So these are the calculations for this first term, t of x1 y1. Now we will go for t of x2 y2. So what will be my t of x2 y2? It will be simply, now we are going to replace this x1 by x2 and y1 by y2. So 1 upon root 2 x2 plus 1 upon root 2 y2 comma 1 upon root 2 x2 minus 1 upon root 2 y2 norm square. So which is further equal to norm of, now simply subtraction. So subtraction of this term and this term. So what you are going to get here? So the first coordinate will be 1 upon root 2 inside the bracket x1 minus x2 plus 1 upon root 2 again, and inside y1 minus y2, this will be the first coordinate, comma the second coordinate will be 1 upon root 2 x1 minus x2 plus 1 upon root 2. Now it will be minus y1 and this minus will be plus. I'm talking about this minus and minus will be plus, so it should be plus y2. So plus y2 bracket close norm square. Okay, so ह्या ओपन साठी हा क्लोज आहे. It represents a point in R2. Okay, so therefore this is equal to, now you can say this is our x1, the entire one, because, and this is our x2, the second coordinate of the point, because what we are having, norm of this x1 x2 whole square is nothing but what, x1 square plus x2 square. So this formula we have to use. So therefore this will be inside the bracket 1 upon root 2 x1 minus x2 plus 1 upon root 2 y1 minus y2 square of this plus inside the bracket 1 upon root 2 x1 minus x2 plus 1 upon root 2 minus y1 plus y2 and what, square. Okay, so just I will erase it out. This was simply for understanding. Yeah, so which will be further equal to, now simple calculations. So therefore this is equal to, so square will be 1 upon 2 x1 minus x2 whole square plus 1 upon 2 y1 minus y2 whole square, and this will be plus twice ab, so plus 2 multiplied by half, right, because this 1 upon root 2 multiplied by 1 upon root 2 will be 1 upon 2, and this will be x1 minus x2 multiplied by y1 minus y2 plus, now the calculation for this term, so it will be half x1 minus x2 whole square plus half minus y1 plus y2 whole square and plus twice ab, so it will be 2 multiplied by half x1 minus x2 multiplied by y1 minus y2, so it is minus y1 plus y2, right. So which is further equal to, so just I will increase one more step. So there is no need of writing this step, but simply for understanding, because in the last example we have skipped this step. So it will be half x1 minus x2 whole square plus again half. Okay, so this term and this term I am combining together, so plus half x1 minus x2 whole square. Next this term and this term, so you will get plus half y1 minus y2 whole square plus half, okay, this minus y1 plus y2 whole square is same as y1 minus y2 whole square plus, now this 2 and this 2 will get cancelled out, so we will get simply x1 minus x2 and what, y1 minus y2, and over here also this 2 and this 2 will get cancelled out. Now I will take this minus sign out from this minus y1 plus y2, so we'll get minus x1 minus x2 multiplied by y1 minus y2. Therefore what will happen, this term and this term will get cancelled out. So therefore what we are going to get, just little more space, so this is equal to so this will be simply x1 minus x2 whole square and plus y1 minus y2 whole square, and this is nothing but norm of z1 minus z2 whole square. Therefore what we have proved, in other words, therefore norm of t of z1 minus t of z2 whole square will be equal to norm of z1 minus z2 whole square for all z1 z2 belonging to R2. Now let us take positive square roots. So by taking positive square roots on both sides, so therefore norm of t of z1 minus t of z2 will be equal to norm of z1 minus z2 for all z1 z2 belonging to what, R2, and therefore t is an isometric. 1 and 2, we can say that t is an orthogonal linear transformation. In paper don't write OLT, okay, and here we have used theorem, so we are supposed to state that in the exam. So that's it. So these two examples are for homework. I will check it in the next class. So that's all for this lecture. Thank you.